Hi, oceanography students. We are now going to start the topic of plate tectonics. And this first lecture is going to introduce you to plate tectonics and give you the basics of plate tectonics. And then there will be a couple of other lecture videos as well as some other informational videos that you'll watch this week as well. Okay, so we originally talked about how our oceans formed on our early planet, and the process that formed those oceans is actually quite different from the way that our oceans are forming today. So we're going to learn how our oceans form today by learning about the theory of plate tectonics. So this is a theory, so it is widely accepted by the scientific community. All right, so before we talk about what plate tectonics are, we need to be reminded that our Earth is made up of layers because this is essential to understanding plate tectonics. So here we have an image that shows you the Earth with a big chunk missing, basically taken out so that you can see from the center of the Earth out towards the surface of the Earth. All right, so remember that we've got the core, and the very inner part of the Earth is called the inner core, and it's a solid structure. You move out a little bit, and then you have the outer core, and the outer core is actually a liquid structure, so it does flow. And then we move out another layer, and we have what's called the mesosphere. Here it's written as lower mantle and upper mantle, but we're just going to call that whole thing the mesosphere. And then we get to the asthenosphere, which flows, okay? And then at the very surface, we have the lithosphere, which is the cool outer shell of our planet. Now this image here is showing you how we define the layers based on what makes them up on this right side here, and what their physical properties are on the left side, okay? So again, we've got the inner core, which is highlighted here, and it says it's solid, like we just talked about. Then we go out another layer, and we have the outer core, which flows, says it's molten. Then we have the mesosphere, which is solid. And then we have the asthenosphere here, which is, it says it's deformable, which means that it flows essentially. Now, all of those, the asthenosphere, the mesosphere, the outer core, and the inner core, those are all hot, okay? The lithosphere is cool, okay? And then this is reminding you that we've got what we call the crust, because it's made up of mostly granite and basalt. Then we've got the mantle, and then we've got the core that is mostly iron. So because the center is hot, basically the hot stuff rises up to the lithosphere or towards the crust, okay? And when it comes up to the cool asthenosphere, it hardens and new crust or new lithosphere is created. And in doing so, it pushes old lithosphere away. And by doing that, it can actually cause our continents to move and the geography of our planet to change. So this is what our Earth looked like 199 million years ago. As you can see, all of the land is stuck together for the most part. So now when I hit play, we're going to see what has happened since that time. All right, so you can see that the geography on Earth is changing. And as we'll talk about in a little bit, these lines here represent spreading areas or areas where crust is colliding together also. Okay, so now it's starting to look a little bit more like our Earth, and you can see India moving up until it will finally end up being attached to the rest of Asia. Okay, so plate tectonic theory describes this process and describes essentially that our continents move, our geography changes, and the reasons why our geography changes. So the theory of plate tectonics states that the outermost portion of Earth is composed of rigid plates that move horizontally in relation to one another. And it describes the reason why this happens. So now we're going to discuss the crust. So this image shows you the inside and the layers, and then it shows you on the right side what it looks like, what the crust looks like. And the crust, again, is the lithosphere. So it's two terms basically referring to the same general area. So the crust then sits on top of the mantle, or you could say that the lithosphere sits on top of the asthenosphere. Okay, now remember that the asthenosphere is hot and it moves, so it's almost as if the crust is sort of floating around on top of the asthenosphere. That's not entirely correct, but that's kind of it's a good image to put in your head. All right, so there are two types of crust. There's crust that makes up our continents, and we call that continental crust, and there is also crust that makes up the ocean, and that is called oceanic crust. After you watch this video, I would like you to watch the video that discusses the different types of rocks, because that gives you a good idea of plate tectonics and will help you as you go along. Okay, so again, there are two types of crust. Continental crust consists of mostly aluminum and silica, whereas oceanic crust consists of magnesium and iron. The continental crust is older because oceanic crust is constantly being produced. That's the type of crust that comes up and hardens, like I was mentioning previously, and you have heat coming up from the inside of the Earth and coming up to the lithosphere of the crust, and it hardens. That hardened new crust is oceanic crust. And if oceanic crust, if there's new crust being created, then someplace else crust has to be destroyed, and that's also going to be oceanic crust. So the oceanic crust ends up being a lot younger because old crust has already been destroyed, whereas continental crust doesn't get destroyed. It stays, for the most part, on our planet. Scientists or geologists in particular don't fully understand that yet, and it could be that some continental crust is in fact destroyed over time, but for the most part what's being pulled down back into the depths of our planet is oceanic crust. Now, because of what they're made up of, continental rocks tend to be less dense than oceanic basalts are. So what that means is that, remember that they're sitting on top of this kind of fluid flowing material that makes up the asthenosphere. So if continental rocks are less dense, they're going to sit up higher than the oceanic rocks will. So the oceanic rocks will sit down lower, which will give us depressions. So the term that describes this phenomenon of things kind of situating deeper or lower when they're floating is called isostasy. So isostasy is the balance of portions of Earth's crust which rise or subside until their masses are in equilibrium, floating on the denser plastic mantle below. Okay, so you can think of lithospheric plates float on the asthenosphere, and as the asthenosphere flows and moves, those lithospheric plates flow and move as well. So we can reference isostasy by thinking about what happens if you place a bunch of blocks that have different thicknesses into water. So differences in the thickness and the density of the blocks cause isostatic adjustment. So we can see over here in this little image, we've got all of these blocks that are different sizes, and therefore the blocks that are smaller are going to sit, are not going to rise up as high, and they're also not going to sink down as low. Whereas these really long blocks, they're going to sink down much lower, and they're also going to rise up higher. They're not going to sit as low. Okay, and you can compare that to crust versus the continental crust versus the oceanic crust. So with the continental crust, it's much lighter. So even though it's thicker, it doesn't sit as deep on the asthenosphere as it would if it was the same density as the oceanic crust. Now the oceanic crust is very dense, and so it sits a lot deeper than it would be if it was made up of the same material as the continental crust, okay? So because it's dense, it sits lower. So the same occurs with the lithosphere. Denser crustal material sinks deeper into the mantle or the asthenosphere than lower density crustal material. Okay. So what we end up with on our planet, because of areas where you have heat coming out and forming new rocks and areas where old rocks are being destroyed and going back into the earth, we end up with what we call lithospheric plates. And where two lithospheric plates meet, we have a plate boundary. Now the boundary is there and the plates are defined by the direction that they're moving. So a plate boundary is a boundary between two lithospheric plates. A plate is made up of crust that all moves in the same direction. So we basically define the plate boundary according to the ways that the two plates on either side of it are moving. And so in this image here, the arrows are actually indicating which way the plate is moving. So you can look at the arrows on either side of a plate boundary to define what type of plate boundary it is. So now we're going to talk about what the three general types of plate boundaries are. The first one is divergent plate boundaries or divergent zones. This is where you have two plates that move away from each other. And in that original image I showed you, here's an example of that. You can see here is a plate boundary. So we've got a plate on this side and we've got a plate on this side. And this plate is moving this way and this plate on this side is moving that way. Because they are moving away from each other, we call that a divergent plate boundary. So here's another image to show you that. And this is similar to figure 3.16D in your textbook. So again, on the top, we've got the lithosphere or the crust, and below we've got the asthenosphere or the mantle. The heat is rising up and causing new crust to form. And what that does is it pushes away the older crust away from that, what we call a spreading center or a divergent zone or boundary. Okay, so this whole line right here would be your divergent boundary. This on the left would be one plate. This would be a different plate because they are moving in opposite directions. We call that a divergent boundary. Okay, an example of a divergent boundary is seen on our planet here. So to orient you, I've labeled the continents that are seen. So we've got North America up here, South America down here, Africa, and Europe. And you should become familiar with what those continents look like so you can recognize them without them being labeled. And you see this line right here. This is actually in the middle of the Atlantic Ocean, and it represents a divergent boundary. Okay, so this is an area where plates on the left side of it are moving towards the left, and plates on the right side of it are moving towards the right, or more appropriately, plates on the western side of it are moving towards the west, and plates on the eastern side of it are moving towards the east. So they are moving away from each other or separating, and that creates a divergent boundary, which is shown as this kind of underwater mountain chain, which we'll talk about in a few minutes. The second type of plate boundary is called a convergent plate boundary. In a convergent plate boundary, plates are moving towards each other or converging. So I've highlighted an area here. So here is a plate boundary. So you've got a plate on the left side, a plate on the right side, and you can see that the arrows are pointing towards each other, which means that those two plates are running into each other. And here's another view of that. So again, here's the asthenosphere down below. Here's the crust or the lithosphere up above. And you've got two plates. They're moving in opposite directions, so they can't possibly be the same plate. So we've got one plate here. We've got one plate over here, and they're moving towards each other, which creates a convergent boundary or a convergent zone. And when those happen, which we'll talk about in the next lecture video, when that happens, a number of conditions can occur. You could have one plate being subducted down below the other one, or they could be colliding and both of them end up rising up. So an example of a convergent boundary that we see kind of close to here is a convergent boundary off of the coast of Oregon and Washington. So in this image here, so there's Seattle here, this is Washington up here, this is Oregon down here. This is the North American plate over on the eastern side, or the right side of this plate boundary. On the left side of the plate boundary is called the Juan de Fuca plate, and you can see you have arrows pointing together, which is showing that this boundary would be convergent because the Juan de Fuca plate and the North American plate are converging or colliding with each other. The third type of plate boundary is called a transform fault, and this is quite different from the other two. Instead of having two plates going towards each other or two plates moving away from each other, we have two plates that are running side by side. And so one would be like moving north and the other one would be moving south. So they're not actually like running into each other. Let me show you what I mean here. Okay, so down here we have the asthenosphere again. Up here we have the lithosphere or the crust. And we have a plate boundary right here that gets created because we have one plate that is sliding towards the south, and we have another plate that's sliding towards the north. So they're not exactly like running into each other or separating from each other. Instead, they're kind of just sliding past each other. An example that we see on our planet is the San Andreas Fault. Okay, so the plate on the left side or to the west of the San Andreas Fault is moving toward the northwest, while the plate on the right side or the east side is moving toward the southeast. Because these two plates are sliding past each other, a transform fault is created where they interact. So here we have our transform fault highlighted in red, and these little black arrows are showing you the direction of movement. So at some point, Los Angeles will be much farther to the northwest, and places over here like San Jose will be much farther towards the southeast. Okay, so they're highlighting those arrows. All right, so on this map here, we have a little more realistic view, and it's showing you some examples of what I just showed you. So we've got the transform fault right here. That's the San Andreas Fault. You've got the divergent zone, again, in the mid-Atlantic, middle of the Atlantic Ocean. And we've got a convergent zone along the west coast of South America, which we'll talk about in more detail in the next lecture. The one that I pointed out was this convergent zone up here. Okay, so now here is a more realistic image than what I was showing you earlier on of the actual plate boundaries. So this image contains a lot of information, so I want you to take a few minutes just to understand everything that you can, everything that's being shown to you, okay? So I want you to take a minute to identify the parts of this map. The tectonic plate boundaries are drawn on it. So you can see these, basically these red lines or these blue lines are showing the boundaries. So that seems to be what's most prominent, but I want you to look below them so that you can see the continents underneath. For example, here's North America. You can see North America there. You can see South America. So I want you to sit with the image for a few minutes and identify the land masses. So where's North America? Where is South America? Where is Eurasia? Where is India? Where is Antarctica? And where is Australia? So I want you to pause the video now until you have identified those continents, those land masses. Next, I want you to identify the oceans. Where is the Pacific Ocean? Where is the Atlantic Ocean? Where is the Indian Ocean? Where is the Arctic Ocean? And where is the Southern Ocean? I want you to pause the video until you've identified those. And then finally, or next, I guess I shouldn't say finally because I have more for you to look for. Next, I want you to identify the general motion of each of the geographical regions you just identified by looking at the plate boundaries and the arrows. Okay, so down here, this little legend is showing you what the different lines mean. So if you got a line that has little triangles on it, I like to call them like they look like shark's teeth. that is identifying a convergent boundary. So for example, over here, the red lines that are kind of jagged, those represent divergent boundaries, so such as right here. And all of your straight blue lines represent transform fault boundaries. The big arrows are showing you the direction of the movement. So I want you to pause the video until you're ready to proceed once you have identified the motion of all of those locations. Okay, so next, I want you to notice that many of the plates that you identified or that you now see by looking at the plate boundaries, many of those plates are actually made up of both continent and land. For example, we have over here the North American plate, which has part of the Atlantic Ocean and North America on it as well. The African plate over here includes part of the Atlantic Ocean, the whole continent of Africa, as well as some of the Indian Ocean over here. I also want you to notice that entire continents move in the same direction, but oceans, the entire ocean, oftentimes does not all move in the same direction, because usually continents are all on the same plate. That's sort of like what makes that a continent. Whereas an ocean has multiple plates to it, right? Look here at the Atlantic Ocean. We've got South American plate, we've got the African plate, we've got the Eurasian plate, we've got the North American plate, and you've got the Caribbean plate all the way in here as well. So the oceans usually have differing directions. Look over here in the Pacific Ocean. Okay, so this is all of this outline here is all Pacific Ocean, but you can see lots of different arrows going lots of different directions. Okay, so the oceans are going to kind of have, depending on where in the ocean you're looking, maybe moving in a different direction than a different part of that same ocean. Okay. You can see that the Nazca plate right here in the Pacific Ocean is moving this way, but when you look at the Pacific plate, it's moving in the opposite direction, okay, which is what is creating this divergent boundary right here. All right, so that leads us to the next thing. And the next thing I want you to do is identify one place that represents a divergent boundary, identify one place that represents a convergent boundary, and finally identify one place that represents a transform fault boundary. And I want you to pause until you have identified all of those. Okay, now you don't need to post these comments in your weekly discussion. This is just an exercise for you to make sure that you can recognize what's going on here before we proceed. All right, so again, here we have North America, here we have South America, here we have Europe and Asia, here's India, here's Africa, here's Australia, and here's the rest of Asia over here, okay? Pacific Ocean is right here. The Atlantic Ocean is here. The Indian Ocean is all of this over here. Up here is the Arctic. Down here is the Southern Ocean. And I think I forgot to tell you to identify Antarctica also. So down here is Antarctica, in case you didn't already notice it, all right? So if you have any questions on this, I would love to help you. So please don't hesitate to contact me before we, get into more detail. Okay. So why does this moving? Why does the motion happen? Like, why are some plates moving in one direction, some plates are moving in other directions? All right. So it's basically because the heat in the mantle is not even. You've got more heat coming up in some places, and then we have it kind of cooling in other places. So basically what happens is that heat comes up from the hot center or the core of our Earth, and when that molten rock gets up to the cool lithosphere, so the cold surface of our planet, the molten rock cools and hardens, and that creates new lithosphere or crust. Now you've got a heated zone right here where that rose up and created new crust all along the surface of our planet in this long line here. So the heated zones traverse a large part of our Earth's surface. So it does not just occur in a single little plume of hot molten lava coming up. So it's not like just one single volcano. It's in basically this long like a long row of kind of volcanoes, basically. Okay, so the new crust that is created pushes the old crust away. So now it's moving away from where the new crust was created, moving opposite directions from this divergent boundary right here. That's what this is being created, is a divergent boundary. Now, because new crust was created and it pushed old crust away, our planet's not going to grow in size. Instead, what's going to happen is that old crust is eventually going to sink back down into the Earth and melt and essentially be destroyed. Okay, so older oceanic crust is returned to the mantle, and in this way, what we have created is a convection cell, or two convection cells, I guess I should say. All right, so we've got the area where the heat is rising up. It's creating new rock and pushing old rocks away. Those old rocks are eventually going to sink down below at what would be considered a convergent boundary, right? You've got a plate right here. You've got this plate over here. They're colliding with each other right along here. So this is the convergent boundary. And one of them ends up basically being denser. And so it sinks down below the other one and it gets destroyed. And that sinks and causes what's called a convection cell. Okay? So the process of plate tectonics is responsible for mountain ranges. Mountain ranges are formed by convergence and also transformed faults. It is also responsible for earthquakes. We experience earthquakes along those plate boundaries, whether they be divergent boundaries or transform fault boundaries or convergent boundaries. That's basically how earthquakes occur. Volcanoes on continents are due to plate tectonics. So this is basically due to convergence, and we're going to talk about the specific types of convergence in the next lecture. Islands, or volcanic islands, I should say, are created by way of convergence, as well as a new thing that we'll talk about called hotspots. And of course, very importantly, plate tectonics creates our oceans by way of divergence or divergent boundaries. Okay, so if you have any questions, please post them under the weekly discussion. Also, please post the following information under your weekly discussion as well. I want you to name the 3 plate boundary types and state the motion around each of those boundaries. We will go on to talk about different plate boundaries in the next lecture and how oceans and different geological features are formed. All right, and thank you.